Hello students, welcome back. Today's video is based on some natural phenomena chapter 12, class 8. Before starting this video, please like and subscribe to my channel LinkedIn Farmer. Let's start. Introduction on some natural phenomena. Natural phenomena are captivating occurrences in the world around us that often defy easy explanation. From the mesmerizing dance of the northern lights to the raw power of volcanic eruptions, these events remind us of the Earth's dynamic nature. Studying these phenomena not only deepens our understanding of science but also fosters a sense of wonder and awe for the beauty and complexity of our planet. Lightning. Lightning is a dazzling natural phenomenon that occurs during thunderstorms. It's a sudden and powerful discharge of electrical energy within the atmosphere, typically between a cloud and the ground or between two clouds. The rapid movement of charged particles creates a brilliant flash of light, accompanied by a distinct rumbling sound called thunder. Lightning's unpredictable and breathtaking display serves as a reminder of the immense forces at play in the Earth's atmosphere. The sparks that Greeks knew about. The ancient Greeks were acquainted with the captivating phenomenon of lightning, which they believed to be the result of the interactions between the gods of thunder and the mortal world. This dazzling display of electricity in the sky, often accompanied by the rumbling thunder, intrigued and sometimes terrified them. While their understanding was steeped in mythology, their awareness of lightning marked an early recognition of the awe-inspiring forces of nature that continue to captivate and intrigue us to this day. Charging by rubbing. Charging by rubbing, also known as triboelectric charging, is a fascinating natural phenomenon where objects become electrically charged after they are rubbed against each other. This occurs because the friction between the two materials causes the transfer of electrons, resulting in one object gaining a positive charge while the other gains a negative charge. This concept has numerous practical applications and historical significance. For instance, amber in cloth. The ancient Greeks discovered that rubbing amber, fossilized tree resin, with wool or fur would cause the amber to attract lightweight objects like feathers. This was one of the earliest recorded observations of triboelectric charging. Balloon and hair. Rubbing a balloon against your hair or clothing can generate enough static charge to make the balloon stick to walls or ceilings. The balloon becomes negatively charged, while the surface it sticks to acquires a positive charge. Van der Graaf generator. This electrostatic generator uses the principle of rubbing to accumulate and store a large amount of electric charge on a metal dome. The charge buildup can create impressive lightning-like sparks when discharged. Photocopiers. The process of electrophotography, commonly known as xerography or photocopying, involves the transfer of toner particles, charged powder, onto a paper surface using electrostatic forces. Triboelectric charging plays a crucial role in this process. Static electricity. Everyday occurrences like shuffling across a carpet and then receiving a small shock when touching a metal object demonstrate triboelectric charging. The friction between your shoes and the carpet causes charge separation, leading to a buildup of static electricity. Electrostatic precipitators. These devices use triboelectric charging to remove particulate matter from industrial exhaust gases. Charged plates attract and collect the particles, improving air quality. Charging by rubbing has not only contributed to our understanding of electricity but also finds practical applications in a wide range of fields, from electronics to manufacturing and beyond. Types of chargers and their interaction. There are two types of electric chargers, positive and negative. These chargers interact through the fundamental force of electromagnetism. Let's delve into their characteristics and interactions. Positive charge, plus, objects with an excess of protons, the positively charged subatomic particles, possess a positive charge. When two objects with positive charges are brought close together, they will repel each other due to the similar nature of their charges. Negative charge, objects with an excess of electrons, the negatively charged subatomic particles, carry a negative charge. Similar to positive charges, negative charges also repel each other when they are brought close together. The interaction between positive and negative charges follows a different pattern. Attraction. Positive and negative charges attract each other. This is due to the nature of electromagnetic forces. Electrons are drawn toward areas with a deficiency of electrons, positive charges, and vice versa. Neutral objects. Objects that contain an equal number of positive and negative charges are considered electrically neutral. Their overall charge sums up to zero, and they do not exhibit significant electrostatic interactions with other neutral objects. Law of conservation of charge. This fundamental principle states that electric charge cannot be created or destroyed, it can only be transferred from one object to another. In any interaction, the total charge remains constant. Charge transfer. When two objects come into contact, electrons can be transferred between them due to friction or other interactions. The object that loses electrons becomes positively charged, while the one that gains electrons becomes negatively charged. Coulomb's law. This law describes the quantitative relationship between the magnitudes of charges, their distance apart, and the force of attraction or repulsion between them. Mathematically, the force between charges is directly proportional to the product of their magnitudes and inversely proportional to the square of the distance between them. The intricate dance of positive and negative charges forms the foundation of electromagnetism, shaping everything from the behavior of electrons in circuits to the structure of atoms. Understanding the nature of these charges and their interactions has paved the way for numerous technological advancements and scientific discoveries. Example: electric charges come in two types, positive plus and negative. These charges interact through the fundamental force of electromagnetism. Let's explore this interaction with an example. Imagine two small objects, one with a positive charge, plus Q, and the other with a negative charge, Q. When these two objects are brought closer to each other, a fascinating interaction occurs. Attraction. Due to their opposite charges, the positive and negative charges attract each other. This attraction is a result of the electromagnetic force. Electrons in the negatively charged object are drawn toward the positively charged object, and vice versa. Force calculation. The force of attraction between the charges can be calculated using Coulomb's law. It states that the force, F, between two charges, Q1 and Q2, is directly proportional to the product of their magnitudes and inversely proportional to the square of the distance, r, between them. Transfer of charge. The transfer of electric charge is a fundamental process in which electrons, the negatively charged subatomic particles, move from one object to another. This movement can occur through various mechanisms and has profound implications in the world of electricity and electronics. Let's delve into the concept of charge transfer. Mechanisms of charge transfer. Friction. When two objects rub against each other, electrons can be transferred from one object to another. The object that loses electrons becomes positively charged, while the one that gains electrons becomes negatively charged. An example is rubbing a balloon against air, causing the balloon to become negatively charged and stick to surfaces. Conduction. Charge transfer can occur when two objects come into direct contact. Electrons move from the object with higher electron density, negative charge, to the one with lower electron density, positive charge, equalizing their charges. This is commonly observed when you touch a charged object, and you feel a slight shock. Induction. This process involves the rearrangement of charges within an object due to the influence of an external charged object. The presence of a charged object near a conductor can cause the separation of charges within the conductor, resulting in a temporary charge imbalance. Importance of charge transfer. Electrostatics. Charge transfer is responsible for the creation of static electricity. When charges accumulate on an object due to friction or other processes, they can remain localized until they are discharged. Electric current. In electrical circuits, the controlled movement of charges forms an electric current. This movement of electrons through conductors allows for the transmission of electrical energy. Electrochemical reactions. Charge transfer is fundamental in processes such as electrolysis, where chemical reactions are driven by the movement of electrons between substances. Electronic devices. Charge transfer is the basis for the operation of electronic devices like batteries, capacitors, and semiconductors. These devices rely on controlled charge movement to store and transmit information or energy. Power generation. The movement of charges in generators produces electric currents that can be harnessed for power generation. Understanding charge transfer is crucial for comprehending the behavior of electric fields, current flow, and the operation of various electrical and electronic devices. It's a cornerstone of modern technology and plays a central role in our everyday lives. Electroscope. An electroscope is a device used to detect the presence of electric charges. It consists of a metal rod with a set of lightweight metal leaves attached to its bottom end. When a charged object is brought close to the metal rod, it induces a separation of charges in the leaves. The light charges in the leaves repel each other, causing them to spread apart. This divergence of the leaves serves as a visual indicator of the presence and type of charge on the object. Understanding charge transfer and its effects on objects is crucial for comprehending the behavior of electric fields, current flow, and the operation of various electrical and electronic devices. It's a cornerstone of modern technology and plays a central role in our everyday lives. The story of lightning. Lightning, a breathtaking natural spectacle, is the result of powerful electrical discharges within the Earth's atmosphere. This electrifying phenomenon has captivated human imagination for centuries, inspiring awe and curiosity. Let's journey through the story of lightning. 1. The charged atmosphere. As the sun heats the Earth's surface, it causes the air near the ground to rise and cool. This process forms cumulonimbus clouds, towering masses of water vapor, ice crystals, and air molecules. Inside these clouds, various particles collide, creating an environment where electrons are stripped from atoms, leading to an accumulation of charge. 2. Charge separation. Within a thundercloud, charge separation occurs. Ice crystals and graupel, soft hail, gain positive charges as they rise to the top of the cloud. Simultaneously, raindrops and smaller ice particles gain negative charges as they fall towards the bottom. 3. Electric fields build. The charge separation generates intense electric fields within the cloud. These electric fields cause positive charges to gather at the top of the cloud and negative charges to accumulate at the bottom. 4. Lightning formation. When the electric fields become strong enough, they ionize the air and create a conductive path between the positive and negative charges within the cloud. This conductive path is known as a stepped leader. 5. Lightning strike. The stepped leader descends from the cloud, seeking a path of least resistance to the ground. As it approaches the Earth's surface, it creates a path of ionized air, creating a visual precursor to the main lightning strike. 6. Main lightning bolt. Once the stepped leader connects with a positively charged object on the ground or another negatively charged region within the cloud, a massive discharge of electrical energy occurs. This is the main lightning bolt, characterized by its intense brilliance and immense power. 7. The flash in thunder. The rapid movement of electrons creates the brilliant flash of light we perceive as lightning. The immense heat generated by the lightning bolt causes the air to expand explosively, creating shock waves that result in the booming sound of thunder. 8. Return stroke. After the initial lightning bolt, the path is briefly ionized. The movement of charge reverses direction, creating the return stroke. It is this return stroke that gives lightning its characteristic flickering appearance. 9. Lightning's impact. Lightning strikes can cause devastating damage, starting fires, damaging structures, and even posing a threat to life. However, they also play a vital role in nature by helping to balance the Earth's electrical charge and aiding in the nitrogen cycle by producing nitric oxide. 10. Continuous wonder. The story of lightning continues to fascinate researchers, who study its intricacies to better understand its formation, behavior, and the potential to harness its energy. In the ever-unfolding story of lightning, the interplay between electrical forces, atmospheric conditions, and the power of nature itself continues to ignite our wonder and deepen our appreciation for the captivating phenomena that shape our world. Lightning safety. Lightning is a powerful natural phenomenon that poses a serious risk to individuals and structures. Practicing proper lightning safety measures is crucial to minimizing the potential dangers associated with thunderstorms. Here's a guide to staying safe during lightning events. 1. Stay informed. Keep an eye on weather forecasts and alerts before heading outdoors. Thunderstorms are often accompanied by lightning, and being aware of their likelihood can help you plan accordingly. 2. Seek shelter. When you hear thunder or see lightning, seek shelter immediately. Enclosed buildings with wiring and plumbing provide the best protection. Avoid small sheds, open structures, and isolated trees. 3. Stay indoors. Stay indoors until at least 30 minutes after the last observed lightning or thunder. Lightning can strike even when storms seem far away. 4. Avoid electrical devices. Avoid using electrical appliances, corded phones, and plumbing during a thunderstorm. Lightning can travel through electrical and plumbing systems, posing a danger to anyone using them. 5. Stay away from windows. Stay away from windows, doors, and concrete walls, as lightning can enter through these pathways. Keep curtains and blinds closed to prevent glass from shattering if struck. 6. Outdoor safety. If you're caught outdoors during a thunderstorm, avoid open fields, hilltops, water bodies, and tall isolated objects. Seek lower ground and crouch down on the balls of your feet to minimize contact with the ground. 7. Avoid water activities. Swimming, boating, and other water activities are especially dangerous during thunderstorms. Water is an excellent conductor of electricity, making these activities extremely risky. 8. Car safety. If you are in a car, stay inside with the windows rolled up. The metal frame of the car provides some protection from lightning strikes. Avoid touching metal surfaces inside the car. 9. Avoid conductive materials. Stay away from conductive materials like metal fences, power lines, and railroad tracks. These materials can carry lightning's electrical charge over a distance. 10. Lightning position. If you are in a group outdoors, spread out to reduce the risk of multiple injuries if lightning strikes the ground. Avoid huddling together. 11. Post-storm safety. After the storm has passed, wait for a minimum of 30 minutes before resuming outdoor activities. Lightning can still pose a threat even after the storm has moved on. 12. Lightning safety indoors. While indoors, it's safe to use electronics, but avoid using corded phones and stay away from plumbing. Such protectors can provide an added layer of protection. 13. Lightning safety for pets. Ensure your pets are brought indoors during thunderstorms. Just like humans, animals can be at risk from lightning strikes. Remember, lightning is a powerful force that demands respect. By following these lightning safety guidelines, you can significantly reduce the risk of injury or harm during thunderstorms. Prioritizing safety and staying informed can help you enjoy the wonders of nature while minimizing potential hazards. Do's and don'ts during a thunderstorm. Outside. 2. Seek shelter in a sturdy building or a fully enclosed metal vehicle, with windows rolled up, as soon as you hear thunder or see lightning. Avoid open fields, hilltops, tall trees, water bodies, and metal objects, which increase your risk of being struck by lightning. Crouch down on the balls of your feet to minimize contact with the ground if you can't find shelter. Keep your head down and cover your ears. Don't stay in open areas like golf courses, swimming pools, or picnic spots during a thunderstorm. Avoid standing under isolated trees or near tall objects, as they can attract lightning. Refrain from using umbrellas, fishing rods, golf clubs, and other objects that can act as lightning conductors. Don't lie flat on the ground. This increases your exposure to the ground's electrical charge. Inside the house. 2. Stay indoors and avoid using corded phones, electrical appliances, and plumbing during a thunderstorm. Keep away from windows and doors to avoid potential glass shattering due to lightning strikes. Close curtains and blinds to minimize the risk of broken glass. If you have pets, bring them indoors to keep them safe. Don't. Avoid using wired electronic devices like corded phones and computers. Don't touch electrical outlets or plumbing fixtures, as lightning can travel through wiring and pipes. Lightning conductors, surge protectors. 2. Use surge protectors to safeguard electronic devices from power surges caused by lightning strikes. Install a lightning protection system, lightning rods, on tall structures like houses and buildings to divert lightning safely to the ground. Don't avoid relying solely on surge protectors. They offer some protection, but not absolute immunity from lightning-related damage. Don't attempt to install lightning protection systems yourself. Consult professionals for proper installation. Remember, thunderstorms can be dangerous, and lightning strikes are a serious threat. Always prioritize your safety by seeking appropriate shelter and minimizing your exposure to potential risks. Following these do's and don'ts can significantly reduce the chances of harm during thunderstorms. Earthquakes. An earthquake is a natural geological phenomenon characterized by the sudden shaking of the Earth's surface caused by the release of accumulated stress along faults and tectonic plate boundaries. This seismic activity can have significant impacts on the environment, structures, and human lives. Here's an overview of earthquakes. 1. Tectonic forces. The Earth's lithosphere consists of several large and small tectonic plates that float on the semi-fluid asthenosphere below. These plates are in constant motion due to the convective currents within the mantle. As plates interact, they can collide, pull apart, or slide past each other, leading to stress buildup along fault lines. 2. Elastic rebound theory. The stress that accumulates along faults causes rocks to deform elastically. Eventually, the accumulated stress exceeds the rock's strength, leading to a sudden release of energy. This energy release causes the rocks to snap back to their original, less stressed shape. This sudden movement generates seismic waves, resulting in an earthquake. 3. Seismic waves. Seismic waves are vibrations that travel through the Earth in all directions from the point of initial energy release, focus or hypocenter. These waves include primary, P, waves, which are compressional waves that travel faster, and secondary, S, waves, which are shear waves that follow P waves. Surface waves, which travel along the Earth's surface, are the slowest and often cause the most damage. 4. Measuring earthquakes. The magnitude of an earthquake is measured on the Richter scale or the moment magnitude scale, milieu. These scales quantify the energy released during an earthquake. The intensity of the shaking experienced at a specific location is measured using the modified Macaulay intensity, MMI, scale. 5. Effects of earthquakes. Earthquakes can cause a range of effects, including ground shaking that can topple buildings and cause landslides. Surface rupture along fault lines, displacing the ground. Tsunamis if the earthquake occurs under the ocean. Liquefaction, where water-saturated soil temporarily loses strength and behaves like a liquid. Ground subsidence or uplift due to changes in stress. 6. Preparedness and safety. Being prepared for earthquakes is essential. Secure heavy furniture and objects to walls. Have an emergency kit with food, water, medical supplies, and other essentials. Know the safe spots in your home and workplace. Have a communication plan with family and friends. 7. Seismic monitoring. Seismologists use seismometers to monitor and record earthquakes worldwide. This data helps researchers understand earthquake patterns and improve preparedness. Earthquakes are natural events that remind us of the dynamic nature of our planet. Understanding their causes, effects, and safety measures is crucial for minimizing their impact on lives and communities. What is an earthquake? An earthquake is a natural geological event characterized by the sudden and rapid shaking of the Earth's surface. This shaking is caused by the release of accumulated stress along faults and tectonic plate boundaries within the Earth's crust. Earthquakes vary in intensity, from minor tremors that are barely perceptible to catastrophic events that can cause widespread destruction and loss of life. The energy released during an earthquake generates seismic waves that propagate through the Earth, causing the ground to vibrate and producing the shaking sensation felt by people and structures. The study of earthquakes, known as seismology, helps us understand their causes, effects, and patterns, contributing to better preparedness and mitigation strategies for regions prone to seismic activity. What causes an earthquake? An earthquake is caused by the sudden release of accumulated energy within the Earth's crust. This energy release is primarily a result of the movement and interaction of tectonic plates, which make up the Earth's outer shell. Here's a more detailed explanation of what causes earthquakes. Tectonic plate movement. The Earth's lithosphere is divided into several large and small tectonic plates that float on the semi-fluid asthenosphere beneath them. These plates are in constant motion due to the heat-driven convection currents within the Earth's mantle. Stress accumulation. As tectonic plates interact, they can move toward, away from, or slide past each other along faults, which are fractures in the Earth's crust. The movement of plates is not always smooth. Stress builds up along faults as the plates become stuck due to friction and the resistance of rocks. Elastic deformation. Over time, the accumulated stress causes rocks along the fault line to deform elastically, like a rubber band being stretched. During this phase, rocks store the energy from the stress as potential energy. Breaking point. Eventually, the accumulated stress exceeds the strength of the rocks, and they can no longer withstand the strain. This results in a sudden release of the stored energy. The rocks snap back to their original, less stressed state, and this rapid movement generates seismic waves that radiate outward from the point of energy release. Seismic waves in earthquake. The seismic waves produced by the sudden release of energy propagate through the earth, causing the ground to vibrate. These waves can be detected by instruments called seismometers. The shaking of the ground during an earthquake is what we feel is the sensation of shaking. Focus and epicenter. The point within the earth where the energy is released is called the focus or hypocenter of the earthquake. The point directly above the focus on the Earth's surface is called the epicenter. The intensity of the shaking is typically strongest near the focus and diminishes as you move farther away. In summary, earthquakes are caused by the movement of tectonic plates, which leads to stress accumulation along faults. When the accumulated stress exceeds the strength of rocks, it results in a sudden release of energy in the form of seismic waves, creating the characteristic shaking of the ground that we experience during an earthquake. Structure of the Earth. The Earth is composed of several distinct layers, each with its own unique composition and properties. This layered structure plays a crucial role in shaping the planet's geology, geological processes, and interactions with its surroundings. Here's an overview of the Earth's structure. 1. Crust. The outermost layer of the Earth is called the crust. It's relatively thin compared to the other layers and is composed of solid rock. The crust is divided into two main types, the continental crust, which forms the continents, and the oceanic crust, which underlies the ocean basins. The crust is where most of Earth's geological activities, such as earthquakes and volcanic eruptions, occur. 2. Mantle. Beneath the crust lies the mantle, a much thicker layer that extends to a depth of about 2,900 kilometers, 1,800 miles. The mantle is composed of semi-solid rock that exhibits plasticity over geological time scales. It's divided into the upper mantle and the lower mantle. The mantle's convective currents drive the movement of tectonic plates, which in turn influence the Earth's surface features and geological processes. 3. Outer core. Beneath the mantle is the outer core, extending from about 2,900 to 5,150 kilometers, 1,800 to 3,200 miles, below the surface. The outer core is composed of liquid iron and nickel. It is responsible for generating the Earth's magnetic field through a process called the geodynamo effect, where the movement of molten metal generates electric currents that produce the magnetic field. 4. Inner core. The Earth's innermost layer is the inner core, which lies beneath the outer core and extends to the center of the Earth. Despite its incredibly high temperatures, the inner core remains solid due to the immense pressure at that depth. It is composed primarily of iron and nickel. The inner core's intense heat contributes to the transfer of thermal energy within the Earth. 5. Lithosphere and asthenosphere. The rigid outer layer of the Earth, which includes the crust and the uppermost part of the mantle, is known as the lithosphere. The lithosphere is divided into tectonic plates that float on the semi-fluid asthenosphere beneath them. The asthenosphere's ductile properties allow the movement of tectonic plates, driving various geological processes. The Earth's layered structure and the interactions between its different layers give rise to a dynamic and ever-changing planet. This structure influences the distribution of geological features, the behavior of tectonic plates, the formation of mountains and oceans, and the occurrence of geological phenomena such as earthquakes and volcanoes. Seismic or fault zones. Seismic or fault zones are regions of the Earth's crust where tectonic forces have caused significant stress accumulation along geological faults. These zones are prone to experiencing earthquakes due to the release of built-up energy. Faults are fractures in the Earth's crust along which movement has occurred. There are several types of fault zones, each associated with specific tectonic settings. 1. Transform boundaries. These are fault zones where tectonic plates slide past each other horizontally. The San Andreas Fault in California is a famous example of a transform boundary. 2. Convergent boundaries. At convergent boundaries, tectonic plates collide. The intense pressure can lead to thrust faults, where one plate is forced over another, resulting in earthquakes and the creation of mountain ranges. 3. Divergent boundaries. These are fault zones where tectonic plates move away from each other. The Mid-Atlantic Ridge is a divergent boundary where new oceanic crust is formed, often accompanied by volcanic activity. Richter scale. The Richter scale, developed by Charles F. Richter in 1935, is a logarithmic scale used to quantify the magnitude of earthquakes. The scale measures the amplitude of seismic waves produced by an earthquake. Here's how the Richter scale works. 1. Logarithmic scale. The Richter scale is logarithmic, meaning that each whole number increase on the scale represents a tenfold increase in the amplitude of seismic waves and approximately 31.6 times more energy release. 2. Magnitude calculation. The magnitude of an earthquake is calculated based on the amplitude of the largest seismic waves recorded by seismometers. This amplitude is measured in millimeters on a seismogram. 3. Energy release. The Richter scale provides an estimate of the energy released by an earthquake. A magnitude 5 earthquake releases around 31.6 times more energy than a magnitude 4 earthquake. 4. Impact. The impact of an earthquake depends on both its magnitude and proximity to populated areas. Higher magnitude earthquakes can cause more widespread damage, and their effects can be amplified if they occur near the Earth's surface. 5. Modern usage. While the Richter scale is well known, the moment magnitude scale, MALU, is now more commonly used to quantify earthquake magnitude. The moment magnitude scale provides a more accurate assessment of an earthquake's energy release across a wider range of magnitudes. Seismic or fault zones and magnitude scales like the Richter scale are essential concepts in understanding earthquakes. These tools help scientists monitor and assess the impact of seismic events, contributing to earthquake preparedness, safety, and hazard mitigation efforts. Seismograph. A seismograph, also known as a seismometer, is a scientific instrument designed to detect and record the vibrations and ground motions caused by seismic waves generated during earthquakes or other seismic events. This device plays a crucial role in monitoring and studying the Earth's internal processes, providing valuable data for understanding seismic activity and improving earthquake preparedness. Here's an explanation of how a seismograph works. Components and operation. Seismic sensor. The core component of a seismograph is the seismic sensor, which consists of a mass, pendulum or spring-mounted weight, attached to a fixed point. When the ground vibrates due to seismic waves, the mass tends to remain stationary due to its inertia while the Earth moves beneath it. Frame or housing. The seismic sensor is housed within a sturdy frame or housing to protect it from external influences like wind, temperature changes, and human activity. This enclosure helps ensure that the sensor captures accurate seismic data. Recording mechanism. Connected to the mass is a recording mechanism that translates the motion of the mass into a graphical record. Early seismographs used a pen attached to the mass to draw on a moving paper strip or drum. Modern seismographs often use digital technology to capture and store seismic data electronically. Recording seismic events. Detecting vibrations. When seismic waves travel through the Earth, they cause the ground to vibrate. These vibrations are transmitted to the seismic sensor within the seismograph. Inertial motion. Due to inertia, the mass of the sensor resists moving with the vibrating ground. As a result, the mass remains relatively stationary while the Earth moves beneath it. Recorded motion. The recording mechanism attached to the mass captures the differential motion between the mass and the Earth. This motion is then recorded as a graphical representation on paper or digitally. Seismogram. The resulting graphical record, known as a seismogram, displays the amplitude and duration of the seismic waves. By analyzing the seismogram, scientists can determine important information about the earthquake, including its magnitude, location, and depth. Importance and applications. Seismographs are vital tools for monitoring seismic activity and detecting earthquakes in real time. Studying the Earth's interior, including the properties of the Earth's layers and the behavior of seismic waves. Assessing earthquake hazards and improving early warning systems. Investigating the characteristics of tsunamis, volcanic activity, and other geological phenomena. Seismographs have revolutionized our understanding of the Earth's dynamics and have significantly enhanced our ability to predict and respond to seismic events, contributing to the safety and well-being of communities around the world. Protection against earthquakes. Earthquakes can have devastating impacts on lives and infrastructure, but there are measures individuals, communities, and societies can take to mitigate the risks and minimize the potential damage. Here are some strategies for protecting against earthquakes. If you are at home, stay indoors, move away from windows, exterior walls, and glass doors to avoid potential hazards from shattered glass. Take cover, drop, cover, and hold on. Drop to the ground to prevent being knocked over, take cover under a sturdy piece of furniture like a table, and hold on until the shaking stops. Stay away from doorways. Contrary to popular belief, doorways are not the safest place to be during an earthquake. Seek shelter under sturdy furniture instead. Stay put. If you are indoors, stay there until the shaking stops. Moving during the shaking can put you at risk of falling objects or debris. Beware of falling objects. Secure heavy furniture and objects that could topple during shaking to prevent injury. Stay calm. Keep calm and reassure family members. Panic can lead to accidents and hinder rational decision-making. If you are outdoors, move to open space. If you are outside, move away from buildings, utility wires, and street lights to an open area away from potential hazards. Avoid overhead objects. Stay clear of trees, power lines, and other objects that could fall during shaking. Drop to the ground. If you can't find an open space, drop to the ground to prevent being knocked over. Stay away from buildings. Avoid seeking shelter in buildings, as they could be structurally compromised. Stay calm and keep a safe distance from potential hazards. Do not run in a panic. General earthquake safety tips. Know safe spots. Familiarize yourself with safe spots in your home, workplace, and any other places you frequently visit. Create an emergency kit. Prepare an emergency kit with essential supplies, including food, water, first aid items, and medications. Plan and practice. Have an emergency plan in place for your family, and practice earthquake drills regularly. Secure heavy items. Use earthquake straps and anchors to secure heavy furniture, appliances, and objects that could become projectiles during shaking. Stay informed. Be aware of earthquake risks in your area and stay informed through local news and official sources. Remember that preparedness and quick, informed actions are key to staying safe during an earthquake. By knowing what to do and practicing safety measures, you can greatly reduce the potential risks and impacts of seismic events. Thank you for watching. Please like, share and subscribe.